Okay. Hello, everyone. I wanted to go over the problems that we did with the activity when you guys were working in groups. So, because some of you, well, you only had one problem to do, so you didn't see the other problems. So, I'm going over all the problems to give you just some additional practice. I would suggest, though, that you try to do the problems before I go over the solutions just to practice. So, you may want to pause the video and do the work on the problems and then play the video so you can see if the way you're thinking about the problems are correct. Okay. So here we draw one card from a standard deck of playing cards. If you pick a heart, you win $10. If you pick a face card, which is not a heart, you win $8. If you pick any other card, you lose $6. Explain with mathematics whether it benefits you to play or not. All right. And so note our face cards, i.e. the cards that have faces on them, are jacks, queen, and king. Remember, there are 4 suits. This is just a quick recap. Hearts, spades, clubs, and diamonds. And there are 13 cards per suit. And no jokers. So over here, we've done something like this already, but we have to make a table, probability distribution table that we're going to set up. And let's see, we'll do it as, it's 2 cases that we win, right? So win if they said if we want a heart. So I think when some people, the way that you were thinking about it, you thought that you had to take sort of 2 different cases into question, and you didn't need to do that. Okay, and so gain, and then P of X. All right, and so face card, not heart. Okay. So this is sort of our setup. Now the probability, you may have to think about it a little bit, but we can put in how much we're going to win. So again, if we pick a heart, right, we're going to win $10. If we pick a heart, if you pick a face card, which is not a heart, we win $8. And then if you pick any other card, we lose $6, right? Oh, I put those in the wrong spaces. So we win 8 if it's a face card, not a heart, and then we lose $6, right? So now thinking about the probabilities, there's 52 cards total, right? So it might simplify, but we know in general, so we might end up with a fraction that simplifies. But we know in general, well, at least we have our denominator right, because we're not including jokers. There's 52 cards in the deck, so the probabilities will be out of 52. We also know that the probabilities, the 2 conditions, right, they have to be between 0 and 1, and they sum up to 1, right? And so here, let's think about this. Well, what's the probability that we pick a heart? This is any heart, right? Any heart you pick, you win $10. Well, there's 13 hearts, right? Because there's 13 cards per suit. The ace through 10, and then jack, queen, king. Okay? All right. So 13 out of 52. Hopefully that makes sense. Well, what's the probability that we pick a face card that's not a heart? Okay? Well, there's 3 face cards per suit, and so there are 4 different suits. So 4 times 3 is 12, but we're taking out hearts altogether. So 12 minus 3 is what? 12 minus 3 is 9. So 9 out of 52. Okay? And then everything else, we lose $6. So the easy way to do that is we can add up 13 and 9 and then subtract 52 from it, right? And so that will leave us with 30. I think I don't know if it was for this problem, but I did see some students no, maybe, I don't think it was for this one, because I was going to say list like all the different possibilities. That would just take a long time to do. I think that was with the dice problem. I saw that. Okay. And so for our expectation, all right, so it is 10 times the probability, 13 out of 52, plus 8 times 9 out of 52, minus 6 times 30 out of 52, which will give us 11 over 26, or about 42 cents. So the question is, explain with math whether it benefits you to play. So it does, right? It benefits you to play because on average you can expect to win about 42 cents every time you play. Okay. All right, let's move to our next card game. So this is card game number 2. And again, if you want to pause the video, see if you can work this out, and then come back, I think that would be a good idea, good practice for your exam. All right, so in this card game, you pay $3 to play, so you have to pay $3. The dealer deals you one card. If it is a spade, you get $10. If it's anything else, you lose your money. Explain if this is a fair game. Okay, so setup should be pretty simple. We win versus lose, and gain probability. Okay, and so again here, if we get, so win meaning we get a spade in this case, right? And how much do we win? Well, remember we had to pay $3 to play it, right? So we win $7, and then we're gonna lose $3 if we don't get a spade, right? Well, what's the probability of getting a spade? 13 out of 52. And then the probability of everything else would be 52 minus 13, or 39 out of 52. Okay. Again, making sure that when you're finished, that P of X, that row, should sum up to 1. Okay. And so our expectation is 7 out of 13 times 13 over 52 minus 3 times 39, 50 out of 52. And that's going to give us -1/2. Double check, because, I can make mistakes, so make sure you're double checking your answers, of course. And if you have any questions, you can ask them in class. So the expectation here is -50 cents, right? So no, it's not a fair game. And in fact, you can, on average, expect to lose 50 cents every time you play. Okay. Next game. So a casino game costs $4 to play. You draw one card from a deck. If it is a heart, you win $10. If it is the queen of hearts, you win $50. Is this a fair game? Explain why or why not. So again, there's sort of 2 different times we can win, and the probabilities as well as the outcome. So if you have a case where the payment is different, depending upon a different outcome, then you don't have to do 2 different tables or 2 different charts. You can put it on the same chart because it's still the same game, right? And so here, if we pick any heart, not any heart, we could say heart, no queen, right? All right, so any heart, no queen, then how much does it say we're going to win? And you don't necessarily have to, well, you do if, let me say this, although it could be clear, because if you put the payments and the probabilities, I can assume it might be nice to make a note if you have wins in the same game, depending upon 2 different options, right? So in this case, you win a certain amount if you have a heart, no queen, but then you win something else if you have a queen of heart, right? You actually win, well, it costs $4 to play, so you're going to win $46 if you get the queen of heart. And then how much will you win if it's just a regular heart? You win $6, right? Because again, it costs you $10 to play the game, so you have to consider that. And then anything else, you lose $4 because you don't win anything, okay? And let's think about the probabilities. Now, what's the probability of getting a heart but not a queen? So we have to take the queen out because that's a different category, right? So that's 12 out of 52. So it's not 13 out of 52, it's 12 out of 52. The probability of receiving a heart or pulling a heart is just 1 out of 52, right? Because there's only one queen of heart. And then everything else, so again, adding up 12 and 1, and then subtracting that from 52, and we're going to get 39 out of 52. Okay, so our expectation is 6 times 12 over 52 plus 46 times 1 out of 52 minus 4 times 39 out of 52. And so this gives us negative 19 over 26, which is about negative 73 cents. So is this a fair game? It's not a fair game, right? Because you're going to lose on average 73 cents every time you play. Okay. Moving on to the dice games now. Okay. So here we have Casino Brown. So proposes the following game of chance, and I put that in there twice, so just admit that. So you roll a fair die, all right? If you roll a 1, then Casino Brown pays you $25. If you roll a 2, you get, if you roll a 1, you get $25. If you roll a 2, you get $5. If you roll a 3, you win nothing. If you roll a 4 or 5, you have to pay $10, and if you roll a 6, you must pay $15. Is this a fair game? Now, since it doesn't say anything about you having to pay, so you don't have to pay. However, as we can see, if you roll a 4 or 5, if you roll a 4, 5, or 6, you owe money, right? So you're in the hole there. So let's look. Let's see what's going on in this game. So here we do consider the random variables. We're looking at a die, so the options are 1, 2, 3, 4, 5, and 6. And again, just reading the directions, just read and reread to make sure you understand how to break down the problem. So let's go back over this. If we roll a 1, okay, then, let me say this too before we go back over in terms of game. Unlike the previous games with the card games, unlike these card games where it was easier to figure out this column, for our dice game, it's actually the probability, or at least in this first dice game, the probability we can fill in right now, right? Because it's a fair die. So this probability will be 1/6 across the board. Okay, 1 out of 6. And so now let's go back and reread to see how much we either gain positively or gain negatively, right? So if we roll a 1, we get $25. So we gain $25 if we roll a 1. A 2, we gain $5. A 3, we gain nothing, so that's 0. A 4 or 5, we have to pay the casino $10, so we lose $10, right? And then if we roll a 6, we lose $15, okay? So for our expected value, since the probabilities are all the same, we can just factor out that 1/6, right? We did something like this in an example in class. And then we just put our gains. So it's 25 plus 5 plus 0, although we really don't need to write 0, minus 10, minus 10, minus 15. And that will give us a negative 5/6, which is about negative 83 cents. So this is not a fair game. Okay, we're going to expect to lose 83 cents every time we play. All right, dice game 2. Now here, and I think I had a typing error too, so let me cross something off. A player rolls a die and receives the number of dollars equal to the number of dollars. See, yes, it's too many equal to the number of dollars. So the number of dollars equal to the number of dollars, cross that off, on the die, except when the die shows a 6. If a 6 is rolled, the player must pay $6. If you want the game to be fair, how much should it cost to play? All right, and again, fair means to break even. All right, so we have to, let's look at this. So again, it's a fair-sided die. So 1, 2, 3, 4, 5, 6. Gain. And our probability, which similar to die game 1, it will be 1/6 across the board. Okay. Now let's see. Let's go back and read. So a player rolls a die and receives the number of dollars equal to the number of dollars on the die, except when the die shows a 6. If a 6 is rolled, the player must pay $6. So I'm going to go and fill that negative $6 in then now. And then everything else is just going to be whatever we land on, right? So we get that money. So the expectation, let's see, 1, 6, 1 plus 2 plus 3 plus 4 plus 5 minus 6. And that's going to give us 3/2 or 1.5. So to break even, so right now, as the game stands, it's not a fair game, but it's not a fair game in our favor, meaning on average, we can expect to win $1.50 every time we play. So the question is, well, how much should it cost to play to break even? Well, if we can expect to pay to gain $1.50 every time we play, then that's how much the game should cost. So thus, the game should cost $1.50 to play in order to break even. All right, so hopefully that makes sense. One last problem and then we're done. All right, so here, if you roll a 2, 3, 4, 10, or 12, you win $5. If you roll a 5, 6, 7, 8, or 9, you must pay $5. Find the expected value. Is this a fair game? All right, so I want you to do this one on your own. And what I will tell you is that you should receive your expected value at about a negative $1.67, which means it's not a fair game. But I want you to check. So see if you can set it up and see how I receive this answer. If you're not clear or you have questions, you can ask in class. All right, we're actually done now.